So you can start if you are ready.
Okay, hi, I'm Riku Arakawa, a PhD student from Carnegie University. I'm excited to talk about our project, PrISM-Tracker, a framework for procedure tracking using smartwatch. We perform numerous procedures or sequences of steps in our daily life, such as cooking, crafting, and even COVID-19 tests. If we make mistakes, such as forgetting one step or doing it in the wrong order, it will lead to negative consequences. For example, we don't want to eat samosa when we forget adding salt. The goal of our project is to develop an intelligent system that can guide users through various procedural tasks. This project started for a specific medical procedure task, which is self-care after mouth surgery, which is a surgical excision technique to achieve high cure rates for skin cancer. Skin cancer is the most common malignancy in the United States, and most skin cancer patients are elderly. They are overwhelmed by the multiple steps in written instructions. For 1 week, at multiple times per day, they needed to perform a series of steps properly. It is a big clinical challenge that elderly patients often do not perform this self-care procedure properly, causing additional infections. Thus, lowering the chances of infection and maximizing patients' independence is an important application of our project. As a first step, in this paper, we focused on tracking user behavior in various procedural tasks using smartwatch. In the literature, there are systems developed for specific tasks such as cooking. In Mimicook, they use depth sensor and embedded sensors to track and navigate user behavior during cooking. Since they require specialized equipment, it is hard to be applied to a variety of procedural tasks. On the other hand, we have seen many techniques about human activity recognition, especially using smartwatch's microphone and motion sensor. Our lab presented a model named Samosa, sensing activities with motion and subsampled audio in the last UbiComp, presented by Vimal Mollyn. Hi Vimal, he is sitting there. And we expected that such human activity recognition can be a plausible method to track user behavior in different kinds of tasks. That's our expectation. Okay, so let me show you how bad his model is actually. So we applied Samosa model to the clinical self-care task, consisting of 12 steps. The frame-by-frame accuracy of tracking steps was 27%. Okay, so to be honest, his work is great. This result means that there's still a gap before we can leverage human activity recognition. So why is current human activity recognition insufficient? First, the dataset tested in human activity recognition often involves coarse and independent activities with striking sensor signals. However, in procedure tasks, data in steps is sometimes not very different from each other. Moreover, steps are performed continuously without explicit start and end time. Therefore, in this work, we propose PrISM-Tracker, procedural information from sound and motion, that can augment existing human activity recognition for procedure tracking with two things. One, graph-based procedure representation, and a user interaction module to handle model uncertainty. This is an overview of the proposed framework. Let me walk through it. The first part is a conventional human activity recognition for frame-level multimodal sensing. We use Samosa's backbone as a feature extractor and train the random forest model to classify sensor signals into steps. But as I have shown, the accuracy of this frame-level prediction is low. Thus, we introduced a graph-based module to increase the accuracy. The graph embeds the user transition information, such as transition probability between steps and how long they spend at each step on average. This information is used by our proposed algorithm as a post-process to obtain more plausible output, which is an extension form of what's called Viterbi algorithm. In detail, the model periodically updates the probability distribution represented in its hidden states based on the transition graph and frame-level sensor observation. Let's see the result. Recall if we just apply human activity recognition as a frame-by-frame prediction, the accuracy was low. If we add the transition graph module, the accuracy gets significantly improved to 51%, where the graph helps the system narrow down the possible prediction. But still, there are some uncertainties. In particular, those steps with less striking sensor values are confused by the model. Therefore, we further propose a human-in-the-loop approach, which we call interactive oracle request. This is basically a real-time prompt from the user, human. We call it the oracle because in the current study, we did not check how accurate the prompt itself is, and we assume that the human prompts are 100% accurate. In this work, we have prepared different human prompts, such as tell me where you do X, or what are you doing? X is a step of interest or uncertainty. For example, X can be washing hands before cooking. No doubt, different prompts impose different cognitive load on users, which we are currently investigating as a future work of this study. Our algorithm we propose in this paper optimizes the timing to ask these prompts to improve the overall tracking accuracy. Here, I only share the result of tell me when you do X prompt. In this graph, y-axis is the average tracking accuracy, and x-axis is the number of human prompts. Summarizing the results so far, the red dotted line is a result without the transition graph, and the blue dot at x-axis 0 is a model with the transition graph. This is a result of the human prompts. As the number of human prompts increases, the accuracy also increases. Even a few human prompts increase the accuracy significantly. We made the implementation public on GitHub to help developers make their own system. Not only the trained model, the framework also outputs useful information, such as the relationship between the number of human prompts and the expected error reduction to understand the trade-off. Or it also tells us how each modality contributes to the accuracy at each step. We also publicized a data collection app used in our study. In the study, we tested our framework in 2 tasks, latte-making and in-clinic wound care task. The clinical task was performed by actual patients with average age 70. Different tasks have different transition graphs. In this figure, each block represents a step. For the latte-making, the above one, the graph has many branches, meaning that different users do the tasks in a slightly different way, but still has some order constraints. On the other hand, for the wound care task, the graph does not have a branch, meaning that the step order was strictly followed. I hope to discuss more about the comparison of these 2 tasks, especially how the difference in the graph's complexity affects the performance. For future work, we are currently developing a real-time interactive system and investigating its effect on user behavior with actual patients in the clinical scene. That's all, and my great collaborators Hiromu, Vimal, and Suzanne will be at the poster session later, so please check it out. Thank you.
Thank you very much, Riku. So I congratulate him that he has three talks in this conference. But okay, let's move to the next speaker. But during that time, you can have one question on that microphone if you have, or please raise your hand. Okay, come to the place.
Hello. So you're using HMMs, right, with normal HMMs. So my understanding with, if you use a normal HMM, you're basically applying a geometric distribution prior on how long you spend in each state. Have you considered, there's actually variants on HMMs, like extensions which allow you to apply priors, like Gaussian priors on how long you actually spend doing each activity. Have you tried something like that, or?
Yeah, that's a very good point. We have tried a couple of different algorithms, and now so far I could say like HMM works the best. But there are many other possibilities as you suggested. We didn't check GMM structure, so I definitely want to chat with you more about the idea.
Yeah.
Thank you.
Thank you.
Okay, let's thank the speaker again. Thank you. Okay, Before going to the next talk, maybe let me remind you that you can also use the Hoover app to give the questions, okay? And if we have a time, then